Hello everyone and welcome to lecture. Today's lecture will be generalizing some concepts from Calculus 1 and multivariable calculus. Specifically, we'll be looking at the total derivative, also known as the Frechet derivative, of a single variable function, a multivariable function, so this is some review, as well as generalizing those ideas to functionals. Which is one of the primary goals of this course, because we want to be able to extend many of the ideas from Calculus 1 and Calculus multivariable calculus to these functionals in an effort to be able to do things like set the derivative of a functional equal to 0 and understand more about what it takes to optimize maximize or minimize functionals. In an effort to provide a clear exposition to how we define the Frechet derivative or the Frechet differential for infinite dimensional vector spaces, we first want to start by understanding exactly what the derivative is, the differential is, for a single variable function and then for a multivariable function. So some of the standard types of functions that you see in Calculus 1 and in multivariable calculus in order to develop a clear picture of how to generalize these concepts to a functional. For a function of real numbers, or from R to R, you most likely learned in your Calculus 1 class or in a more advanced analysis class that the first derivative exists if the following limit exists. And you define the derivative of a function at a point as the limit as h goes to 0 of f of x plus h minus f of x over h exists, if this limit exists. Graphically speaking, this number, if it exists, corresponds to the slope of the tangent line at a point, at the point x. And so this is a picture of what this is saying. If this limit exists, the slope of this tangent line at this point x is what you might have been taught the derivative is. In terms of the epsilon delta definition of the existence of this limit, this is the same thing as saying for all epsilon greater than 0, there exists a delta greater than 0 such that if the absolute value of h is less than delta, then the absolute value of this difference quotient, f of x plus h minus f of x over h minus this number, f prime of x, is less than epsilon. And essentially this is what we have in many Calculus 1 courses, and this is a workable definition for the definition of a single variable derivative of a single variable function. However, when it comes to generalization and generalizing this idea, it's actually a little bit more helpful to write the definition in a slightly different manner. Specifically, because h is a real number here, in the sense that h is the increment that we're taking the limit of as h goes to 0, the so-called limit of the secant line. If we multiply both sides of this expression by the absolute value of h, or you can think of this as pulling out an h from this term right here, the 1 over h from both sides, and multiplying both sides by the absolute value of h, this definition actually, the conclusion of this definition becomes if the absolute value of h is less than delta, then the absolute value of f of x plus h minus f of x minus f prime of x times h is less than, the absolute value of this difference is less than epsilon times the absolute value of h. And it turns out that this definition of the derivative is actually a much more powerful idea because of the fact that this is an idea that is going to be directly generalizable both for multivariable functions of n variables and more importantly for functionals, so infinite dimensional functionals, or functions on an infinite dimensional space. If we reinterpret this in terms of Taylor series, we can see exactly why. So consider this quantity right here, f of x plus h minus f of x. From calculus 3, we know that under certain conditions on the function f, we can express this difference in terms of a Taylor series. We can write f of x plus h as f, the function at the point x, plus f prime of x times h plus some remainder r, where the remainder depends on h, this difference. Minus f of x. And this is for a fixed value of x. The function evaluations cancel out, and we're just left with f prime of x plus, or times h, plus the remainder term r of h, where this remainder has to satisfy something special. The limit as h goes to 0, or as the size of h goes to 0, of the absolute value of the remainder divided by the size of h. This limit must be equal to 0. And this says that the remainder itself has to be going to 0 faster than h is decreasing to 0. If you go through and kind of parse what this is saying right here in terms of the epsilon delta definition of this limit being 0 means that the limit, or for all epsilon greater than 0, there should exist a delta greater than 0 such that if absolute value of h is less than delta, then the absolute value of r of h over h must be less than epsilon, or the absolute value of the remainder must be less than epsilon times the absolute value of h. But notice what this is saying, and try to connect this to the previous definition of the existence of a derivative. This is exactly what we have here. This expression right here is saying the exact same thing. Essentially, this remainder function, if you kind of subtract f prime times h from this side right here, is exactly this expression right here in the original definition of the derivative from a calculus 1 class. So the idea here is that with the theory of Taylor series, because remember this r of h, this remainder function, if you can express f in terms of Taylor series expansion around the point x, this is just all of the higher order terms in the Taylor series expansion. So the terms of the form h squared, h cubed, h to the fourth, all of those terms in the higher order expansion live in this remainder term right here if the function has a Taylor series expansion. However, it turns out that this expression right here is extremely useful because this is nothing but an increment, total increment of the function f. And what we're saying is that a function has a derivative, or its derivative exists, if there exists a linear function of the increment h, so the domain increment, such that the remainder term is going to 0 faster than the increment is going to 0. And this is the essence of differentiability. In fact, we can redefine differentiability to essentially be this. We say that a function is differentiable if there exists a linear function that approximates the increment in this way. So for instance, if we have the existence of this linear function right here, such that the increment is equal to the linear function plus this remainder, whose limit goes to 0 in this way, then we say the function is differentiable. Note that this is a linear function. This is sometimes called the total differential. Of the function f. It's relatively straightforward to show that this is in fact a unique function. So if there exists a function of the form m times h that approximates this increment in this way, this is going to be unique, and it is the best linear approximation of the function at this point. This is also sometimes called the Frechet derivative of the function. It's a synonymous name for total derivative, and it will be very, very important when we extend this idea to functionals. Before jumping up to the Frechet derivative of a functional, I'd like to also review the differentiability or the total derivative for a function of n variables, so an n variable scalar function, or a function from Rn to R. This is what you typically see in a multivariable calculus course. Hopefully you'll recall from your multivariable calculus course that the Taylor series idea developed before for the increment is actually typically a starting point for defining the differentiability of a multivariable function. Specifically, we say that the Frechet derivative of a multivariable function is a linear function that approximates the increment for small enough values of h. So, for instance, we say that the Frechet derivative, or rather the Frechet differential, can be defined in the following way. We say that the function LF of h is the Frechet differential of the function f if at some point x in n-dimensional space Rn there exists a positive delta such that for all h in Rn, where h is a vector here. This is should be a vector. It's like a variation of the displacement away from x, such that h is small enough or less than delta. We have the following approximation, that f of x plus h minus f of x is equal to this LF function, LF of h plus some remainder function R of h. Now, it's important to note here that this LF must be a linear function. And this remainder term must satisfy the following limit. The limit as the size of h goes to 0 must, of the absolute value of the remainder over the size of h. This limit must go to 0. And if this linear function exists, we call it the Frechet differential. So LF of h is the Frechet differential, and the Frechet derivative is the operator, representation of the operator. It's the actual operator itself. Specifically, we can think about what this is going to be, and it should be clear to anyone who's seen multivariable Taylor series. So specifically, this multivariable Taylor series expansion we're doing for small values of whatever norm we're using in Rn, small less than delta, and we have that f of x1 plus h1, x2 plus h2, all the way up to xn plus hn will be equal to f of x1, x2 up to xn plus all of the partial derivatives, partial derivative of f with respect to x1 times h1 plus the partial derivative of f with respect to x2 times h2 all the way up to partial derivative of f with respect to xn times hn plus some remainder term that depends on each one of these h1s through hn's. But depends on these terms in a very specific way. It depends on these terms in that we can say this is always going to be less than or equal to some constant times the norm of the vector norm of h squared. Or the limit of the absolute value of this remainder term goes to, over the norm, the size h, goes to 0. This is the multivariable Taylor series, and really it's just an extension of the normal 1D Taylor series. So this is something that you would typically see in a multivariable calculus course. However, it's important to note here now that this multivariable Taylor series is exactly giving us this Frechet differential. Specifically, just to make things a little simpler, if we represent this as just vector notation as x plus h, and subtract this term right here, which is just f of x. In vector notation, this is just saying this is equal to the gradient vector of the function f at the point x dot product, the vector dot product with the vector h, plus this r, this remainder term of h, where r of h satisfies this limit right here, because it's just the higher order terms in the Taylor series approximation. So it's all the terms of h1 squared, h1 times h2, h1 times h3, and so on and so forth for all of the multiplication combinations of the components of h. This term right here is a linear function of h, and it's exactly the Frechet differential because of this. It's a linear function, and it's the so-called the best approximation of this increment of the function f. This is why this is a very good example, and it's a suitable generalization of the total derivative from 1D calculus. Where the remainder is just the higher order terms in the Taylor series approximation, and by definition, these terms are going to zero faster than by an order of magnitude in h, the size of h, faster than this linear term is. And this is why we call this the Frechet differential, or total differential, of our multivariable function f, mainly because this is a linear function, and it approximates the increment, the total increment of the function in this way. And I'd really like to show exactly how we get the gradient vector here very naturally from the definition, specifically from the definition of the Frechet differential. We have that the remainder over the norm of h has to go to 0, which means that for all epsilon greater than 0, there exists a delta greater than 0, such that the absolute value, if the norm of h, so if the size of h is less than delta, then the absolute value of r of h over the norm of h must be less than epsilon. Another way of saying this, we can write this as the absolute value of the remainder function, r of h, must be less than epsilon times the size of h. The remainder function itself is the increment f of x plus h minus f of x minus this linear function m dot h, and this must be less than epsilon times h. They're the norm of h, and from this we're essentially done, because now if we fix a given h to be, say, for instance, h is equal to just h1, so variation along the first component, and then zeros everywhere else, this inequality is saying that the function evaluated at x plus h1 times e1 hat, which is the unit vector in the e1 hat in the first direction, minus f of x minus m1 times h1, because the dot product m dot h is m1 times h1, is less than epsilon times the norm of h. And we're done, because this is giving us the first component of m1 must be the first derivative of the function. This entire thing is the increment with respect to the first coordinate in the first coordinate direction. So this m1 times h1 is exactly equal to the partial derivative of the function with respect to the first coordinate times h1. and each one of the other coordinates can be recovered by this. But this is even stronger. This Frechet derivative is even stronger than saying all the partial derivatives exist, because it's saying that no matter what h is, if the size of h is less than delta, then this limit will exist. So this is why the Frechet derivative is very strong, or the total derivative is very strong. It's basically saying that we have a uniform derivative. This idea can be extended directly to functionals. So suppose we have some functional from some normed linear space into R. We define the Frechet derivative, or the Frechet differential, if it exists, as a linear function, or linear functional, I should say, of the following form. We form the increment, delta j, which is a functional itself, a nonlinear functional of h, as j of y plus h minus j of y. And we say that for the Frechet derivative, is if it exists, or the Frechet differential is the linear functional LF of h that approximates this nonlinear increment with some remainder r of h, such that LF of h is a continuous linear functional, and the remainder goes to 0 as the variation h goes to 0. This norm right here is the function space norm. So it's the norm with respect to this normed linear space. The ratio r of h over the norm of h, the size of the variation h, has to be equal to 0. Note that this limit statement is in terms of the norm. It means for all epsilon greater than 0, there exists a delta greater than 0, real numbers, such that if the size of h in the function space norm is less than delta, then the difference between the increment, delta j, and the linear functional, LF of h, has to be less than epsilon, because this remainder is just this increment minus the linear term, or the linear approximation. So it's really incredible that this definition extends directly from even just the one-dimensional scenario, but you can see the connection as well to the multivariable Frechet derivative. This linear function is sometimes called the Frechet differential, or total differential of the functional. In terms of this functional, we can also call it the variational derivative, total derivative of the functional, or the total differential of the functional. And it's sometimes noted as lowercase delta of h, or delta j of h, to denote that it's a linear functional of the variation h. And for functionals that we're considering when we do, say, like the Histogram problem and other forms of the simplest variational problem, our integral functional is I. Recall that we were dealing with I of y being equal to the integral from, say, a to b of f of x, y, y prime, where f is a multivariable function of x, y, and y prime. I'd like to go through and show what this is going to be, and it turns out that under some relatively simple assumptions on the function y, we have a very, very nice result. So this functional, the total increment of this functional, delta I of h for any variation h, is going to be the integral from a to b of I of y plus h, which will be f of x, y plus h, y plus h, y prime plus h prime dx, minus the integral from a to b of f of x, y, y prime, which is the same thing as the integral from a to b of this f of x, y plus h, y prime plus h prime, minus f of x, y, y prime dx. Now we note that if f is a smooth enough function, so this multivariable function is a smooth enough function, we can consider the multivariable Taylor series expansion of this smooth enough function, or taking the Frechet derivative of the multivariable function instead of the functional. So remember that from what we previously discussed, that the multivariable Taylor series of a functional, or of a function of n variables, is just the linear part of this increment. So it's the derivative times the increment added together for each one of the coordinate directions. So what that means is that this expression right here is the same thing as the integral from a to b of f y, the y partial derivative of f evaluated at the point x, y, y prime, times h, plus f y prime, the partial derivative of f with respect to y prime, times h prime, plus r of h comma h prime. Where r is the remainder in this Taylor series approximation. So r is a term that goes to 0, with respect to the norm of h, the function h. This is square root of h squared plus h prime squared if we use the 2 norm, because this is the Taylor series expansion with respect to h and h prime. So this has to go to 0 as h squared plus h prime squared goes to 0. And so we can separate this out into what this is using the linearity of integration. And specifically, this is going to be the integral from a to b of fy times h plus fy prime times h prime dx, plus the integral of r, and this is exactly the remainder functional from above, depending on h. It's this expression, we'll call it rf to distinguish it from the previous expression, from this r. This is our rf in this approximation formula for the Frechet derivative. And this thing right here is a linear functional. It's exactly LF of H, or the first variation of our functional, our integral functional. This is exactly what what form the first variation takes, which is pretty incredible, because essentially what we now have is the integral of this expression being an expression for the Frechet differential, or the total differential of a functional of this form, of a functional that takes the form of an integral. And this is an incredible thing, because essentially it's all obtained using basic calculus, and we now have an expression for what it means to take the first variation of a functional. And to connect this with the finite difference method that we applied a little earlier, Eulers finite difference method, we can go to something very interesting. If we do integration by parts on this term right here, recall that if you take the x derivative of fy prime times h, this is going to be the same thing as the x derivative of fy prime times h plus fy prime times the derivative of h, which is h prime. So if we use this product rule and do integration by parts here on this term, we obtain another expression for delta j as the integral from a to b of fy minus the x derivative of fy prime times h plus this term right here, the integral of the derivative of this, because we're doing integration by parts here, and the integral of the derivative of this is just this evaluated at the boundary points. So fy prime times h evaluated at the boundary b and a. So this is a slightly, a slightly closer expression to what we obtained for the using the finite difference method from Euler, but it's a little bit different in that this is an integral expression. We're integrating over this thing that we obtained via the finite difference method from Euler, plus some terms in the boundary evaluated at b and evaluated at a. And in general, when we're dealing with the simplest variational problem, where the variation is 0 at the boundaries, this term drops out. It goes to 0 because h, the variation, is 0 at both of the boundaries. We expect, will be shown in the next part of this lecture, that at a maxima or a minima of this functional delta j, if it has a continuous first variation functional, at a minima we expect the variation, so at minima or at maxima, we expect the variation delta j first variation to be 0, in direct analogy to the single variable case and also to the multivariable case. So this is what we'll show in the next part of the lecture. And doing this, setting this delta j equal to 0, gives us the expression that this integral has to be equal to 0. And this approach here was Lagrange's approach towards analyzing the variation and solving this problem for the Histogram problem. After setting this equal to 0, Lagrange then said that because this integral was equal to 0, this function fy minus d dx fy prime has to be equal to 0. And this will give you, in general, a second order differential equation for the solution to your variational problem. However, it was pointed out by Euler that one could not make this logical jump immediately this fast. One needed to prove that if this integral was equal to 0 for all h, then that necessarily implies that the function should also be equal to 0. And this is the so-called Lagrange's lemma, which I will prove in the next part of this lecture.